Once each vector is resolved, separated into its components, the respective x, y, z components are added to determine the components of the resultant vector. So we're separately adding the x components, separately adding the y components, and separately adding the z components to find the components of the resultant vector. So let's take this scenario as an example. Coplanar forces, F1, F2, and F3 all lie in the xy plane. So the vectors themselves, F1, F2, and F3, are all shown in blue dashed arrows. Their x and y rectangular components are shown in solid black arrows. So using Cartesian vector notation as we just introduced it, let's go back a second to remind ourselves what that is. This is a vector expression using I hats and j hats, the unit vectors. This is Cartesian vector notation of a force vector. Vector F1 is expressed as F1x I hat plus F1y j hat. Notice the signs are both positive because F1x is in the positive x direction and F1y is in the positive y direction. Vector F2 would be equivalent to negative F2x I hat plus F2y j hat. This one's negative positive signs because the F2x vector goes to the left in the negative x direction and the F2y vector goes upward. And finally, F3 in Cartesian vector notation equals F3x I hat minus F3y j hat. We note that the resultant force vector that we can call F sub r is by definition the sum of all the forces, vector F1 plus vector F2 plus vector F3. So let's simply go to the next step and express each of these forces in their Cartesian forms, F1x I hat plus F1y j hat minus F2x I hat plus F2y j hat plus F3x I hat minus F3y j hat. Then to go to the next line, let's collect scalar coefficients that are in front of I hat only, and then collect scalar coefficients that are in front of j hat only. So we're taking those scalars, F1x minus F2x plus F3x, putting that in front of I hat. And similarly, we have the coefficient in front of j hat as F1y plus F2y minus F3y. That equals the resultant force vector itself, which can be expressed as F sub rx I hat plus F sub ry j hat. The resultant force vector is somewhere in this two-dimensional space, somewhere in the xy plane, and it has its own x component and y component. So what we are seeing, therefore, is that this scalar magnitude of frx, its x component, is by definition the summation of the x components of all the force vectors, summation f sub x. And as we see from these vectors here in their particular directions, that equals f1x minus f2x plus f3x. Also, f sub ry, the magnitude of the y component of the resultant vector, equals summation fy. That equals, for this case, f1y plus f2y minus f3y. So once the components of the resultant vector are determined in the way that we just described, the resultant vector can be sketched in the xy plane. Let's say this is our resultant vector. The magnitude of this vector, which we refer to as italicized, not bold, f sub r, can be found from the Pythagorean theorem, and its direction theta can be found using trigonometry, where theta is between 0 and 90 degrees. So if we have determined the magnitudes frx and fry, let's just use the Pythagorean theorem that we're all familiar with to calculate f sub r, which is the length of the hypotenuse of this right triangle, or this right triangle here. They are identical right triangles. The legs of this right triangle are frx and fry. They have lengths or magnitudes, frx and fry. The hypotenuse has magnitude or length f sub r. We can also calculate theta. Notice that we're showing this sketch in the xy plane. We're defining what angle theta is, because we could also alternatively define this angle to be theta, and then this expression would be different. But if this is how we're going to define theta, it's this angle here between the positive x-axis and the vector f sub r, then we can use inverse tangent, because we know tangent of any angle is the opposite side over the adjacent side, right? So katoa. So theta, therefore, is the inverse tangent of the opposite side, which has magnitude fry, over the adjacent side, which has magnitude frx. Now you do see absolute value bars here, right? Which means inside here, inside this argument of the tangent, is a positive value. There is a good reason for that. The reason for that is so that we get an angle between 0 and 90 degrees, because in this class, for our purposes, we're going to refer to angles as somewhere between 0 and 90 degrees, at least for two-dimensional problems. So in other words, if we have a vector that's in the second quadrant over here, then instead of measuring the angle all the way from the positive x-axis to that vector that would be greater than 90 degrees, we instead are going to simply indicate the angle with respect to the positive y-axis so that the angle is between 0 and 90 degrees. If you don't take the absolute value, which means you could have negatives inside this argument, then theta will be some other value that's not between 0 and 90 degrees. So the reason for those absolute value bars is important to mention. It's so that theta is an angle between 0 and 90 degrees.